Ladies and gentlemen, thank you very much. First, I would like to thank, of course, the organizers in general and Tatjana in particular for inviting me. It's a great honor to be able to speak here. I wanted to talk about a subject of the past years that we worked on, the reason is the following. Because of its relative simplicity and transparency, DUCT acoustics based on the concept of modes is probably the single most important model to understand sound propagation in ducts. We understand the optimization of liners, cut-on, cut-off phenomena, excitation of distortion modes by non-uniform mean flow, Taylor-Sofrin selection rule, scattering of cut-off modes into cut-on modes at sliced liners, and so on and so on. The canonical model of uniform flow is well understood and classic, but much less is known for modes in non-uniform flow. And this is described by the PRIDMORE-BROWN equation. Let me see. This is what I wanted to talk about. After an introduction, a section on a canonical model with some results, and then something about a matching method based on newly available integrals of PRIDMORE-BROWN profiles, and then a little bit on slowly varying modes. Where is PRIDMORE-BROWN is the first question. Well, PRIDMORE-BROWN can be found, let me see if this works. Does this work? Is there a pointer here?
No, because it is a quality of the screen.
Oh. Is there a pointer?
On the screen, pointer doesn't work at all.
Is there a pointer? No?
Yeah, but you can see it.
Oh, okay. Okay, fair enough. The PRIDMORE-BROWN situation is where you have a duct with non-uniform flow, and it's difficult to point it from here. But in the inlet, you have the boundary layer, relatively uniform mean flow, and the boundary layer again. In the bypass, you have a thicker boundary layer, and in the APU, in the back of the engine, in the back of the aircraft, we have a situation with even non-uniform mean flow and non-uniform temperature gradients of this type. And this is everywhere where, well, the non-uniform mean flow in a duct more or less applies as a model. What is PRIDMORE-BROWN? Well, originally PRIDMORE-BROWN is the name of a man, David Clifford PRIDMORE-BROWN, and developed in this paper, which is almost 60 years old, an equation for 2D homotropic model perturbations in a compressible parallel shear flow, and that is now known as the PRIDMORE-BROWN equation, and it constitutes an eigenvalue problem for the modes, but we now call the radially symmetric 3D version also PRIDMORE-BROWN equation, and for the general case for arbitrary cross sections also the generalized PRIDMORE-BROWN equation. The PRIDMORE-BROWN equation is found by a lot of manipulations, which I'm not going to talk about, of course, here, from the linearized order equation that you see here, and for mean parallel shear flow in axial direction, you can rewrite the acoustic field into this equation for the pressure. It looks like a third order equation, but the third order derivative is only included to get rid of the final unknown, so that everything is in pressure. If we substitute modal forms, so solutions of the form e to the power I omega t minus ikx, in other words, you Fourier transform in time and in place, then everything reduces to this equation, and this can be seen as the generalized PRIDMORE-BROWN equation, and is just a generalization of the Helmholtz equation. And for cylindrical symmetry, when we have e to the power I m theta periodicity, then it further simplifies to an ordinary differential equation, which, if you look carefully, is a sister or brother of the Bessel equation. The boundary value problem appears when we take this equation together with boundary conditions, and this gives us a countable set of solutions with index mu. M was already for the circumferential periodicity, and eigenfunctions indicated by Pm mu of r, and the wave numbers, which are the eigenvalues Km mu. No radial wave numbers, as you may be used to, because there's no such thing as a standard solution of this equation. How to make them? Well, to make them is quite a task on its own. I'm not going to talk about this, just a few hints, because this is a computational air acoustics conference. How do we find all modes? That's an important problem. And the idea is to start with a simple configuration, let's say uniform flow, and then do a parameter continuation in impedance and mean flow profile. So we assume that we have them all in this way, and then we can follow them until we find the parameter value that we need. An example is when we do this path following for the impedance, and with this nice animation from my former student. And here you see how the impedance starts at infinity, runs to infinity, and somewhere halfway we may assume that there is the value that we need. And then we see that the eigenvalues start at the crosses, that's the hard wall value, and then they move up to the next value while the impedance parameter varies upward. And note the direction, which is very important. If we start in the bottom and go up, then the values disappear to infinity. If we do it in the other way, then we had to catch them from infinity, which is very difficult. So you have to make sure that you go in the right direction. By the way, this is for an e to the power minus omega t convention, so you have to take the complex conjugate if you want to do it according to the rest of the notation. Note the surface waves, difficult to point that from here, but everywhere where the eigenvalue k, the wave number k, is not near the real or the imaginary axis, the behavior of the function is such that it is located close to the wall, exponentially close to the wall, and we call that a surface wave. And one of the four surface waves that you see here is an instability, which is a problem in its own. These are examples of solutions that you can find, just examples, but I chose them for one particular reason, and that is the following. You see that all these modes, except for the last one, they are all zero at the walls, at the ends. In other words, they're confined to a core, and they are not directly dependent on the impedance value, and that means numerically that shooting is not possible, because you have to shoot from something that you cannot vary. You start from zero. So the numerical solution is to be a little bit more subtle than shooting. I mention this because I first did it always with shooting until, well, I fell in this trap. A very interesting test case to check is the approximation borrowed from quantum mechanics, where the behavior is similar as a quantum mechanical wave function in a potential well, and from quantum mechanics you get the quantization condition based on this WKB high frequency approximation, and this quantization condition turns out to be this integral of the square root, has to be an an even number minus a half times pi, And if you substitute that for the cases just seen, and you compare the approximate and the actual numerical solution, you see that this works quite well. It's very interesting result to use for higher frequencies. Of course, in the end, you don't use it, but it was a nice information. The agreement was excellent. Now, in the end, you get something like this, of course. You get waves, and they propagate to the right, and in the horizontal direction, you see something like 2 pi over k, which is the wave number, is the wavelength, because 2 pi over k is the wave number. An exact model with PRIDMORE-BROWN. PRIDMORE-BROWN has no exact solutions, not simple ones at least, and we tried to make a canonical model which was, in principle at least, complete solvable, not by elementary functions, but by a power series solution, such that at least you have something that can be arbitrarily accurate. And from this arbitrarily accurate solution, we can learn the behavior of certain subtle effects. And it is, in fact, the solution for the Green's function problem, where you have a point source, which happens to be a mass source, which is from the Green's function not well defined, but we chose to have it a mass source, linear boundary layer profile, uniform profile in the center, and then linear on the other side, and a wall lining, an impedance wall. We can solve this, at least in principle, by Fourier analysis in circumferential direction and a Fourier integral in the axial direction. And then in the end, for the Fourier transform, we end up with, again, the PRIDMORE-BROWN equation. And there is a singularity which will be important in a minute. What are the typical properties of this solution? Well, we have acoustic modes, which is exactly what you expect. But there are also hydrodynamic instabilities, similar to what I just noted already in this previous picture, and other surface waves. And there is a so-called critical layers, which is where a continuum of solutions where the phase velocity of the mode is equal to the mean flow velocity. So exactly at that line. And in the as a function of the k value, the Fourier integral value, this happens to become a branch cut of a complex logarithm, which is very, very subtle, and therefore you don't know what to do with it, and that's exactly the reason why we spent some time to analyze it. Now, the acoustic poles are situated by and large like this, maybe a few in the middle, but I didn't draw all the situations. The branch cut from the critical layer is somewhere like that. And then we have, if the source is in the boundary layer, we have a pole somewhere there, and 2 additional poles where one may be an instability if the boundary layer is thin enough. This is not general, but if the boundary is thin enough. And then the integral for the Fourier transformation is something like this, which we can close upward for x is negative, so that we get a summation over backward running modes, and we can close downward for x is positive, so that we get a summation over positive running modes, plus the contribution along the branch cut, which is by itself a problem. So we want to know how to deal with this. Now, if we do that, and all the mathematical details are in the paper, so you can check that, we find for the easy case of a thin boundary layer, source somewhere halfway, and an impedance with the imaginary part in the positive half plane, something very innocent like this. But as soon as we change the impedance to the other side, to the complex conjugate side, and we put the boundary layer, and we put the source in the boundary layer, then we see that the boundary layer produces vortices, which is a bit unexpected, because we know that a force may produce vortices, but a monopole a mass source, how can that produce vortices? Well, it will be able, we will see, but it was something that is only when the source is in the boundary layer. And if we make the boundary layer thinner, further thin, in this case 1,000, but the number depends on the problem, of course, then it appears that there is an instability. And this instability may be excited directly from the source if the source is in the boundary layer, or it may be excited a little bit downstream when the source is not in the boundary layer. But there is always this instability. And this instability is a very serious issue because, it may fill everything, and it's not nice to have to include this. The contribution from the branch cut and its associated pole is very minor unless all acoustic modes are cut off, is one conclusion. And so it makes sense to use the acoustic modes as a complete basis to construct the general solutions. I didn't show that, but you can switch the contribution of the branch cut off and on, and the difference is almost nil, except when the contribution of the modes is so small. So this is a confirmation that we could use the acoustic modes by itself and do not worry too much about the branch cut. We saw trailing vortices in the boundary layer. We saw the relevance of the spatial instability and the related question of the limit when you take the boundary layer to 0. Because if the boundary layer is very thin, why not take it 0? Well, it's known that this has a problem, and we can study this if we consider the complete Pridmore-Browne equation or a related equation based on this. So how physical is this? Well, we did the analysis in detail, and you can say that in general, in any reality, so when we do this, for example, numerically or experimentally, not when we say to the problem, thou shall be only be time harmonic with only fixed frequency, but there it will in general be all kinds of perturbations, and these will excite other complex frequencies. And these other complex frequencies, they one of them may have group velocity 0, and if we take the boundary layer thickness to 0, then we follow the imaginary part of that particular solution, this omega star, the imaginary part, then we see that the imaginary part of this this frequency all of a sudden becomes negative, and therefore it becomes an instability. And since it's an instability with group velocity 0, it's called an absolute instability. It blows up in your where you stand, where you stay. It's not convected with the mean flow. And even worse, the growth rate, the imaginary part, goes to infinity, minus infinity, and therefore plus infinity for the growth rate, for the boundary layer to 0. And that means that the problem for boundary layer to 0 is ill-posed in time. In fact, you cannot take the boundary layer 0, and you have to be very, very careful there. It was only recently found a few years ago by Ed Bremley, and he solved in that way a dispute of almost 50 years. For mass spring damper cyst impedance, dimensional arguments show that the critical thickness, where the boundary layer becomes absolutely unstable, is a function of these parameter times problem parameters times some function f, which is at the moment not important, because if we make a plot, then we see that this function f is, for the greater part of this parameter space, is close to a quarter. So if you take a quarter, then this is a very reasonable approximation, and when you substitute then the numbers from a real industrial liner with a depth of 3.5 centimeter and a real part of 2, etc., then you find that this critical thickness is very, very small. It's less than a hair, 10 micrometers. So what we do is we take the boundary layer thickness 0 and make it ill-posed, while if we make it a little bit thicker than that, then in reality there's no boundary layer instability. So to get rid of our absolute instability and get rid of our ill-posedness, we have to make our problem, regularize our problem with a finite thickness. And this can be done in various ways, and I'm not going to show that here. But this is the idea. Since it's very reasonable to neglect the thickness, but you should not take it 0. You should always be taken a little bit more than that. What we also saw in the problem was the vorticity shed by the source. Now, if we consider the compressible order equations with mass source and force, and we take the curl of this and substitute then the mass equation, then we get in 3D something like this, and we see that the vorticity vector omega is excited, is fed by, in principle, the vorticity of F, the force, which is what you expect. You expect that the force creates for vorticity, but also the mass source, but only if the mass source is coupled with a background vorticity. So it's multiplied by a mean for vorticity. The other term is the term which exists only in 3D, and I'm not going to talk about that now. The vorticity is produced by a non-conservative force field, but also by a mass source in mean vorticity. And in 2D linear shear flow, which is what you have in boundary layers, you can make the equation even a little bit simpler. And what we get here is an equation with a remarkably simple solution in the incompressible limit, which is practically the situation for thin boundary layers. A remarkably simple solution where the vorticity in the z direction is given by this heaviside times the delta function, of course, in the horizontal direction, and this wave part. So that is the trailing vorticity from a mass source in shear flow, and the hydrodynamic wave number K0. You can make pictures of it. Of course, from the vorticity you have to calculate first pressure and the velocity. So there is where the boundary conditions come in. But then you can solve it for pressure and the velocity in free field. And you can do it also near a hard wall. And here you see the effect of the hard wall in the U velocity. And you see this is for an impedance wall. And for the impedance wall, you see particularly the U velocity that it becomes a little bit tilted in some way or another. I cannot explain this further, but you see there the effects of everything. Apart from this, we can also consider this vorticity passing a liner end, a hard-soft transition. And when this silent vorticity, which is not the type of vorticity you have in potential flow, it's vorticity in shear layer, in shear flow. But when this vorticity passes the hard-soft condition, then it scatters a sound. And that is what happens here. Here you see how the vorticity scatters and creates in the far field, because this is the inner field, a sound field which can be given like this. This is a rather subtle calculation. I don't give any details, but we use Wiener Hopf. And a remarkable property of this is that it is essential for this solution to exist, that the shear, the U prime, the derivative, has to be less than the frequency. Only then the problem converges. If the frequency, if the field, if the shear is larger than omega, then the field diverges, which means that you cannot neglect the end of the boundary layer, and so the boundary layer cannot be ignored, and we have to include the end of the boundary layer, which is a much more difficult problem. But in this case, you can situate this let's say at the bottom of the boundary layer, such that we can ignore. Well, and assume that the boundary layer is very thick, so that the top of the boundary layer is far away for the problem. That is not possible for the case of the U prime is large. This is a very unexpected result in a way. So some interim conclusions. A complete solution, including the Bragg-Kutch contribution, is rarely possible. So therefore this canonical situation, which was milked out in detail, and it shows that indeed Pridmore-Brown modes dominate and can be used as approximate basis. The thin boundary layer along the impedance wall becomes absolutely unstable with infinite growth rate for vanishing boundary layer thickness. The problem becomes ill-posed, and a finite boundary layer, although it only have to be very thin, but can regularize this. And a mass source in shear flow produces trailing vortices, and these may scatter and radiate into sound at hard-fault transitions, and the behavior is radically different for low and high shear. Now I would like to talk about another subject which we worked on, and that is the problem of mode matching with PRIDMORE-BROWN. Mode matching with PRIDMORE-BROWN is not trivial, it's not straightforward, for the simple reason that these PRIDMORE-BROWN modes are only available numerically, and so it gives you a box of Pandora to do the whole numerical, to do all the numerical issues. And this box of Pandora made it quite questionable if it was worthwhile in the first place. But in the end we were able to do it in a, well, rather new way, such that it was useful and was very accurate. The motivation was a problem from APU, the APU problem, where we have, and you have to look there, we have a duct with a strong, radially strongly varying mean flow and temperature, such that it is definitely a situation of PRIDMORE-BROWN modes. But at the wall, you see that the wall, there are cavities, where these cavities are there to attenuate the sound, sort of big Helmholtz resonators. But the point is that because of the geometrical restrictions, these cavities change. They change from cavity to cavity, the depth become less and less. So at every section we have another impedance, so we cannot solve the whole thing for once. We have to do it section by section and then connect everything. So this was the natural situation that you have to apply boundary mode matching. Mode matching, so you start in general per section as a sum over mode, typically suited for mode matching approach, and the new and efficient and accurate mode matching method based on exact integrals of PRIDMORE-BROWN's modes is then now to be presented. That was because we first tried the other way and that was not very satisfying. Now some mode matching basics. I do not know if everybody has a picture of mode matching, but it's something like this. You have all these sections, and per section you have a solution in the form of right and left running modes. Same for the velocity. And then at the interface we have a certain distribution of the pressure. And on the other side also, so from continuity of pressure you take the pressure at both sides equal. And the same for the velocity. And when you expand on each side in their modal expansion, we see that, well, this has to be equal for all r. Now that's a lot of points, so what we do is that we take the inner product on both sides with suitable functions. So we make a projection, so to speak, a Galerkin projection. And what we take is then suitable function, for example, Bessel functions or other. What is suitable? Multiply, take the integral, and find in the end a system of matrices and turn everything into an exercise in linear algebra. Now the matrices, the matrix entries are inner products, and these inner products are for non-uniform. The PRIDMORE-BROWN modes have to be determined numerically, but also all inner products have to be determined at all interfaces by quadrature, numerical quadrature. And this, because they are both oscillatory, this gives you, especially for the higher order modes, a very demanding numerical problem. So it looks as if you need a much higher accuracy for the modes than you need for the actual problem. Computing inner products numerically is expensive and less accurate. Question: can we find closed form expressions for the inner product like we can for the uniform flow, because then we have products of Bessel functions and that can be found analytically. Now this is not possible to our knowledge, but can we find another inner product such that there is a closed form? And the answer therefore is yes. So the summary of the new matching method is the classical. We take this inner product, and on the right hand side we also take some inner product, but now the inner product is a little bit more complicated. This integral of p times psi is now turned into something where pressure and velocity, etc., occurs with some weighting functions which are to be determined in a minute. And on the left side you have to do it by quadrature. On the right side we have integrals available which gives you an exact result. So that is the end, and the less is expensive and less accurate, and the right is cheap and accurate, because you do not need anything more than the modes that you had already in the first place. Now, where do we get these integrals from? I'm not going to show that in detail because that's not the place for, but I show you in a very simple situation just to see the flavor of it. Suppose that we have the Helmholtz equation, which is similar but simpler, and another Helmholtz equation of another of the other mode where you want to compare with, and we multiply crosswise and subtract, and we find then alpha squared minus beta squared phi times psi from the second term, and on the right side we have these things, and then we integrate over a cross section. And this integral over the cross section on the right side can be turned via Green's theorem, or Gauss if you like, into an integral over the circumference. So here we have an inner product with the answer is the integral over the circumference. Now the circumference is of course only rarely known, but for circular ducts the Helmholtz equation turns into Bessel functions, and for the Bessel functions we know how they behave, and we can substitute that, and then we have the exact values on the right hand side, because then the integral over the circumference becomes a point. So this is the derivation of the classic integrals of the products of Bessel functions, and exactly the same by analogous manipulations, but a bit more pages of formulas, of course, can be done when we do it for the PRIDMORE-BROWN equation, and we find then in the end this form. And this form is for the generalized PRIDMORE-BROWN equation, and this equivalent for circular symmetric geometry, when the modes are of the form f of r times e to the power I m theta. We have for this vector p, u, v, w, and p is the solution of the PRIDMORE-BROWN equation. We have this result, and this result is the integral, the exact integral of the PRIDMORE-BROWN equation, which can be used as an equivalent of the inner product. It is not exactly an inner product, but it works equivalently. So what we do is we compare the classic multiply quadrature and see what happens, and the new mode matching method, we take now the other inner product based on the new integrals and use the pressure, use the PRIDMORE-BROWN equations as its own test function, and no extra calculations, and everything is in closed form. Now we can compare, because we don't trust, of course, the new thing directly. We can compare. We compared it with these three situations, and when we do the whole thing of the mode matching, etc., in the classic way and the new way, then we find perfect match, no difference. But of course, this is not a real proof. You have to be a little bit more in detail. So here we did it for the pressure along in the radial direction, and we find that really the new and the classic are right on top of each other, which is on its own already a a surprise for other reasons. Similar for the axial and radial velocities. Now, the best test that I always found is a test based on energy conservation. That is the third test, and that is what comes now. If we take an integral over the complete volume, and we turn our energy conservation into a flux over the outside plus an integral over the source terms in the center, then we can calculate the energy, and if the energy, what goes in is equal to goes out, the total energy in integral has to be 0. But of course you make an approximation because you use only a finite number of modes, and we can see how well we approximate 0, because that is 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, etc. when we increase the number of modes. And then we see that they both go nicely to 0, but the new method even faster than the classic one. So the new method is even working better than the old one. Question is, the energy better with more mu modes, and the new method performs better than the classic one. Why is that? Why is the new method even better than the classic one? Well, the explanation is this when we check if the edge condition is satisfied. The edge condition is an a posteriori check. The amplitudes of our modes will behave as a function of the index, something like a negative power of the index, something like 1 over n squared or something in that style. Mu is the index, so it is 1 over mu squared, and q is then has to be less than 0. So it will be something like this. We don't know what exactly, because we do not know the behavior for this impedance wall, be hard soft or impedance, but something like this. So if we take on the left side and on the right side the logarithm, then we can isolate our q, and we find that the q is approximated by the logarithm of the amplitude divided by the logarithm of the index, and this has to approach to our q that we want to check if it satisfies the convergence. Now, at the interface we have the wall, the edge condition, boundary condition is discontinuous, but the field may be singular, but there may not be a sink or source of energy, so the flux must be an integral function, and therefore this q has to be less than -1, so that we have uniform convergence of our series. So we are going to check if q is less than -1, and then we will see something which is also relevant for the convergence of our energy result. And we find the following. We find that the convergence of the amplitudes, well, the power, the q, is very similar for the two methods, the classic and the new, for the 3 configurations. And you see that they follow each other very closely up to the end. And in the end we see that the classic one deviates. The new one is smooth and nice, the end's very nice, but the classic one gives a strange hiccup. All in all, we see that the q is in the order of -2, -1.8, and -2 again. So the edge condition is satisfied, but the convergence of this q reveals the inaccuracy of the classic amplitudes. The new amplitudes are smoother for large index because there's no quadrature inaccuracy, and that explains the energy behavior. Because the last modes in the energy summation are just not accurate, and that is why this is not only faster, but it's also more accurate. So the classic mode matching works, and for uniform flow you have everything in closed form, and that is classic and very useful. But for non-uniform flow it's expensive and less accurate, but with the new method we do not have to calculate anything more than what we did already for calculating the modes, and it's cheaper and more accurate. In fact, the success is in a way too good, because at least far better than expected, because the inner product is not really an inner product, it's not a proper inner product. And so it was a little bit of a surprise that all the modes could be singled out. But in a way, it proves that the contribution of the branch cut is indeed so small that it does not contribute very much to the energy integral. And that is the second conclusion from the why we can take the PRIDMORE-BROWN modes as our basis. All in all, it remains a fine task in functional analysis, but that is not the subject for here. Now I would like to talk, to finish, a little bit about another subject. For potential flow, for potential mean flow, the modes in a mean flow can be approximated by a WKB approximation for a slowly varying duct. And slowly varying duct is a very natural situation because, as we saw the previous, the first pictures, all these ducts that we are dealing with are not straight ducts. All are more or less slowly varying, not fast, but slowly indeed, because of the mean flow conditions. And for the potential mean flow, there was a nice solution, simple, with an exact adiabatic invariant. And the question was always, is there also something like this for shear flow, for the PRIDMORE-BROWN modes? And the answer is yes, but. It is, but not as nice as as for the potential flow problem. And therefore I studied the following problem: a slowly varying duct in shear flow, two-dimensional for simplicity. And you see how the duct walls vary. I take hard walls to start with, and I take a mean flow and perturbations, and this gives you, for the mean flow equations, in fact just the Euler equation, which is a very difficult one, with boundary conditions and some flux that we need to have mean flow in the first place. And the perturbations, the acoustic perturbations, gives you the linearized Euler equations, plus boundary conditions at a hard wall, again of the same type. Now, the slowly varying mean flow can be approximated, but it's not straightforward. There is no such thing as a standard mean flow for shear. Like there is in the quasi one-dimensional gas solution for potential flow. So we had to construct something, but it appears that there is a linear shear flow of this form, linear form, with an analytical solution where this parameter tau and sigma has to be determined. But if you take the ansatz of this form, then there is something possible. We substitute that, now where are we? Hello. We substitute this ansatz in the equations, and we find to leading order these equations, telling that pressure, for example, is a function of x, etc., etc. And it appears that this has a parameterized family of solutions with lambda, an unknown a parameter that you can choose, so that is more or less the shear. And you substitute, and then you find, an algebraic Bernoulli-like equation which has to be solved per x. And then for flux, given flux F and a geometry and this energy constant, we have a mean flow solution, a mean flow approximate solution. This can be substituted in the linearized Euler equations, and we do the WKB ansatz, where we look for amplitudes multiplied by this slowly varying phase, and we find to leading order this system again, in the usual way with the Doppler shifted capital omega. It's not important, you don't have to read it, but it is this method, it's this way. And we find to leading order the PRIDMORE-BROWN equation again. The PRIDMORE-BROWN equation is easier written in this form with an amplitude q and a function psi, which has to be normalized in some useful sense. And to facilitate the analysis, this equation for linear profile can be reduced to Weber's parabolic cylinder equation, and there you have standard software for, and that makes life also easier if you want to do the first experiments when you do not know what will happen. Now, from the usual solvability condition for the next order, we find an equation for this amplitude Q. All very many pages of work. I'm not going to talk about that here. But we find then in the end an equation of this form. And this gives you then the following solution for amplitude Q. In potential mean flow, there is a simple adiabatic invariant leading to an elegant and simple expression for Q. Unfortunately, as I said, that is not the case here, but we have something. And that's probably related to the existence of conserved energy in the case of potential flow. And there's no such thing here. But at least there is this. But it takes some numerical aftercare to get our solution in this case, and it's not as elegant and transparent as for the potential mean flow. Typical examples is SHEAR with a SHEAR parameter of 0.5, density that starts of 1, and some flux, etc., all dimensionless. We take some tanh hyperbolic for the geometry, and then we can calculate the mean flow. The mean flow is given in this form. You see the horizontal component, you see how it's squeezed on the right side so that the average velocity increases a bit, and vertical velocity is particularly in the middle non-zero, and in the rest it's parallel flow again. And here you see the actual wave numbers. You see them on the right running modes and the left running modes on the bottom. And the number 4 is interesting because you see that the from 5, dimensionless number 5, it reduces to a relatively small number, so it almost touches 0, which means that the wave number becomes long. And question is k is 0, is that cut off? I do not know where cut off means here. It's a subject of study yet, because the Doppler shift is at the bottom 0 and at the top is the lot. So where is the Doppler shift going to on average? I don't know yet. Here you see an example of the modes. On the right side you see the cross-sectional profile. You see that the mode does not exist at the top, only at the bottom. Here they exist on both sides. And here you see the third one. And here you see the one where the wave number became close to 0, because you see how it's squeezed in this narrower part of the duct, and therefore the wavelength becomes close to infinity, which would amount to cut off. In the left running, you also have a few, and now it's just the opposite. It's exists on the top instead of at the bottom. And another one is a bit asymmetric in this way. The asymmetry is completely due to the fact that it is a strong shear. Huh? The mean flow is, has a Mach number of 0.9 at the top and 0.2 at the bottom. So it's something which it's very strong, but just for the picture. Slowly varying mean flow of linear shear as analytic solutions, which is a finding on its own, I think. WQB solution of slowly varying modes in linear shear is possible. Turning point analysis to be done. In contrast to the slowly varying modes in potential mean flow, there is no simple adiabatic invariant, and the solution requires some numerical aftercare. But there is at least something. And now the general conclusions of everything. Interaction of sound with mean flow vorticity is to be described when the mean flow has vorticity, so you need shear. And for parallel mean flow, that means that we have PRIDMORE-BROWN modes. So PRIDMORE-BROWN equation is the simplest equation, I think, where you have this coupling. It includes instabilities, production of vorticity by mass source. The ill-posed boundary condition for vanishing boundary condition has to be regularized, which is a direct result of the complete solution, which is again the PRIDMORE-BROWN. Integrals of PRIDMORE-BROWN modes produce an efficient new mode matching method, and slowly varying modes are possible with shear flow, although not as nice as the with the potential flow variant. This was work of the past about 8 years, and I want to acknowledge all the people that have contributed with this, and I thank them for the stimulating and ever-pleasant cooperation. And this is about what I had to say. Thank you very much.
Thank you very much. I think